In this lesson, we're going to learn about similar polygons again, but in this one, we're going to look at calculating the length of missing sides in our two polygons, and we're also going to take a look at using indirect measurement with similar polygons to find heights of things that we can't just directly measure. So I just have our little reminder up here of what similar polygons are. They're polygons where the corresponding angles are congruent and the corresponding sides are proportional. So I have this first example where I want to calculate the missing side lengths in triangle DEF in this case when we look down here. That's the one. But we do notice that our two triangles are similar. We already know that. So since we know they're similar, we know everything that's stated up here. Corresponding angles are going to be congruent and the corresponding sides are going to be proportional. Now, since the corresponding sides are proportional and we need to find a missing side, specifically I'm going to find the length of segment EF. So I need to find, call it D. I'm going to look for which side corresponds to D. Well, I notice that this side I'm calling D is in between vertex E and vertex F. So when I come back to my similarity statement, I know E and F are the last two letters, which have to mean that they're going to correspond to B and C. B and C. Therefore, my 12 is going to correspond to my D. So that's my first ratio that I'm going to set up. I always like to start with my variable. So I'm going to start up with, I'm going to go with D is matching up or corresponding to the 12. So there's my first ratio. Now I just have to find another set of corresponding sides in my two triangles. So I'm going to get rid of all of this and all of this. And then I like to go back and pick a number that I actually know is a length, and that would be our 15 here. Well, then I have to find that corresponding side to the 15. Well, that's in between vertex D and E. So when I look at D and E, that's going to have to match up with A and B. There's my A, my B, so it's going to have to match up with the 20. So I have my two ratios. I know that my sides are proportional, therefore those are equal. And now it's just a matter of solving that proportion, and I'll have it. So I come here and I go, well, D times 20, that's going to put us at 20D. And then when we go 12 times 15, that equals 180. Now, if we divide both sides by 20, we find out that D equals 9. So we just figured out this side length right here is 9 units long. To figure out the length of side E, it's not really going to be any different. Again, I'm going to start with my variable, my E. I always like to start with that, so I know that I have that taken care of. And that's going to correspond then to the 16. D corresponds with A, C corresponds with F. Therefore, the sides in between those two angles have to correspond. 16. And then I know that that's going to have to equal another ratio. Well, I come back over to this one, where we had this ratio of the 15 over the 20. Those sides are still the corresponding sides, so I'm going to use that again, and I'm going to have 15 over 20. And now we just go through and we're going to solve this proportion. So I'm going to cross multiply again. Take E times 20, and we're going to get 20E this time, equal to, but now when we take 16 times 15, we're going to end up with 240. And now if we divide both sides by 20, that's kind of a fat marker, isn't it? I'm going to end up with E equal to 12. And we just found the lengths of those two missing sides in our similar triangles. I have another example here. This time we want to calculate the length of segment AZ, or side AZ. So I look up here and I go, well, that's right here. So I'm going to give this a variable right now. I'm just going to call that X, because that's the piece that we're looking for. Now, what we've been looking at is we've been looking at similar polygons, and in this one, similar triangles. If the triangles are similar, then we could set a proportion, we could solve this. Now some of us look at this and go, but there's really only one triangle here. But there's not. There's really two here. So what I'm going to do is, I have this set up. I'm going to get rid of this to help show us that. Nothing's changed, I just changed the color. So now you see this little triangle in blue, but then there's also the big triangle. So what I'm going to do is I'm just going to pull the little triangle in blue out, and it's right here. Now, with that being said, I'll put that back. Let's put this back. So we have this. I'm going to bring that down so that's kind of in the same spot, just below it. And what that shows us is this part right here, remember, is also 10 inches. All I did is I pulled this triangle out, so that bottom piece of the little triangle has to fit in to this piece right here. Now, that helps us. Here's why. Because now you have this little triangle and this big triangle, but are they really similar? The answer is yes, and here's why. Notice angle M is 90 degrees. Notice angle A is 90 degrees. So we know that those two angles match up. We have one set of congruent angles. But that second set of angles that are congruent is angle R. You see how angle R, right here, call it the blue triangle? But it's also angle R in the big black triangle. So we have our two sets of congruent corresponding angles. We know our triangles are similar. Therefore, we can now set up a proportion to help us figure out our missing side length, which I have labeled as x. And like I've done in the past, I always like to start with my variable. That's my x. Well, which side does that match up with? That's going to match up with my side that's 2 inches. And the reason that it matches up with that one is because angle A is the 90-degree angle, angle Z is my unmarked angle. Angle M from my blue triangle is the 90-degree angle, and angle J is the unmarked angle. So the x and the 2 are between the same two angles, or the corresponding angles, I should say. Now, I set up my other ratio. Now, since I started with the x, that came from the big triangle, so now I find a side in the big triangle that I know. Well, that's that whole bottom side, which is 15 plus 10, which is going to put us at 25. And that's going to be over, well, the whole bottom side in this case of the other triangle. Now, I probably shouldn't say bottom, but I noticed from the black triangle, it's the side that's between the right angle and my little single arc. So I come down to my blue between my right angle and my single arc, and that's the side that's 10 inches long. And now I solve my proportionate, and I'll have that side length figured out. So I'm going to cross multiply here. That's going to put us at 10x. I cross multiply here. That puts us at 50. I'm going to divide both sides by 10. To find out that x equals 5. Now in this case I have labels on it, inches, so I'm going to know that that x is 5 inches long. Or in other words, side AZ is 5 inches long. And I have one more example here. Now this one I want us to calculate the height of a building. And you could actually do this experiment. If you wanted to find the height of something really tall, go out on a sunny day where you can see shadows. That's what I have represented here. I have a person, I'm a great artist, there's my stick person, and then there's the shadow of the person. Then we have the building over here with the building shadow. Now, what's happening is these two figures, the person and the building, along with their shadows, create triangles. So when I look at this one, I have a triangle from the top to the top there. And then in the building, I have the same thing going on where we have a triangle right here. Okay? And those triangles are going to be similar because when the sun's shining, and as long as you measure shadows at the exact same time, this angle here and this angle here are going to be congruent. Now the other part that we have to understand is, or assume, is that this building was built perpendicular to the ground, making a right angle, and this person stands perpendicular to the ground. So now you have two triangles, two sets of congruent corresponding angles, therefore they are similar. So now I can set up my proportion. Well, this is the question mark spot, or the variable spot. I'll leave it as a question mark. So I set up my proportion. I'm going to have that side over, well, now I come down to the person. And the person, it's going to be the 6. And then and that's going to equal, set up my other proportion. Well, I have the side that's 55 from the building, and then, which is the shadow, sorry, and then I have the shadow of the person, which is 4. And now we go through it, we solve our proportion. So we have our 4, question mark, equal to 6 times 55, which is going to be 330. And then we will divide both sides by 4. And we just figured out that our question mark, or the building height, is 82.5. And the label on that is, notice the little apostrophe, that means feet. So we just figured out the height of that building without actually using a tape measure. And that's going to conclude this lesson on similar polygons.